As we continue our treatment of simple harmonic motion, I want to start by letting you in on one of the little secrets of the physics world. And that is that one of the big tricks that physicists like to use is recycling results. So here is a good example of that. If you remember from before, we rearranged Hooke's law and Newton's second law of motion for our mass on a horizontal spring to eventually end up with d squared x dt squared equals minus omega squared x. Now when we did this before, we had a k over m here, and then we figured out that omega squared was k over m. But this is a general pattern. And the idea here is when you look at this, what you should be seeing here is that anytime you've got something of the form second derivative of stuff equals minus crap times stuff, you have a simple harmonic oscillator and the natural frequency is the square root of the crap. What do I mean by that? So it turns out that there's nothing in mathematically, there's nothing in that's especially sacred about these variables being x. Instead of x, actually let me just put it over here. So for instance, instead of x, we could have theta. So we could have an angular variable, for instance. And if I can somehow get an equation into the form where I've got the second derivative of theta with respect to time, and I have a minus sign and a theta, the stuff between the minus sign and the theta would be the angular frequency, and I would have a simple harmonic oscillator. In fact, we can go even further. When you study electricity and magnetism, you'll eventually see this come up again as something that looks like this, where the Q is an electric charge. And again, what you'll have is simple harmonic motion. In that treatment there, you'll call that an LC oscillator. So nothing says this has to be a linear position. It could be an angular position. It could be an electric charge. It could be anything. As long as you see the second time derivative of it equals negative the thing itself and some stuff in between, you have a simple harmonic oscillator, and the stuff in between is the square of the natural frequency. So I'm going to work through some examples of this to show how this kind of thing works. We'll start by thinking about vertical oscillations. So if you were to hang a spring vertically instead of horizontally, what, if anything, changes? So just to have everything defined in a sensible way here, I'm going to go ahead and say that the equilibrium position of my mass is capital X equilibrium when I've got a horizontal spring like that. Now if I hang the mass on the spring vertically, what's going to happen is the spring is going to stretch because of the force of gravity acting on it. And so if this was the old equilibrium length here, this much here now is the new equilibrium length, which I'll call capital X equilibrium prime. And then from this new equilibrium position, we're going to go ahead and take a look at displacements about this equilibrium position. So we'll go ahead and say that this distance here is x. All right. So with that, let's go ahead and take a look at the forces here. I've got gravity down. Oops. I've got gravity down, and I've got my spring force up. And it's going to make sense here. Let's just say down is positive. I think that's going to be the easiest way to think about this. If I go ahead and write Newton's second law for this, I'll have the force of gravity down. The force of the spring will be pointing up. And this will equal ma. Now here, technically I should be putting in a plus sign because I'm going to say minus kx, but remember that minus sign is accounting for direction. Anyway, so it's all good. So mg minus k. Now I'm going to have to think very carefully about my x here. For initially this static situation here where we're just at equilibrium. For at equilibrium, the acceleration is 0. Now, to express this, this will be the stretch that goes into Hooke's law is this distance right here that I've dotted out. So that's going to be x prime equilibrium minus x equilibrium. All right. So with that, what I'm going to do is I'm going to solve for what this position is. So just add distributing through kx prime equilibrium minus kx equilibrium equals mg. I can divide through by k, get x equilibrium prime equals mg over k plus x equilibrium. We'll be using that result in a second. Now, in phase 2 of this, we're going to go ahead and do the same thing, except now we're going to go ahead and disturb this from its equilibrium position. We'll pull it down a little bit and let it go. So now the acceleration will no longer be 0. So we'll have mg minus k times, well, what is this new stretch? This new stretch here, this distance that we're stretched from the original equilibrium, because that's what's going to go into Hooke's law, this distance is going to be x equilibrium prime minus x equilibrium plus this lowercase x for the extra displacement that we have. That's going to equal ma. But I can now take what my x equilibrium prime is and stick that in. So I'll have mg minus k times mg over k plus x equilibrium minus x equilibrium plus x equals ma. Oh, all right. First off, those cancel. And then if I distribute the k through, what do I end up with? I'm going to have mg minus k times mg over k minus kx equals ma. Well, here the k's are going to cancel. Like so, leaving me mg minus mg, and so that cancels. And now I can finally go and start to put this into my usual form. I can rearrange this to say a equals minus k over m times x, and then I can remember that a is the second derivative of x. d squared x dt squared equals minus k over m times x, and I've hit my holy grail equation. Second derivative of stuff equals minus crap times stuff. And whenever I see anything like that, I recognize I have a simple harmonic oscillator, and this piece right here is omega squared. So it turns out that the only thing different between a horizontal and a vertical oscillator is that the equilibrium position changed. we still have the same frequency. And so that's the idea there. We can go ahead, we started by writing Newton's second law for the situation. We took into account the shift and ended up with the same prototype equation. Now, how did I know to do that? In part, it's just because it's a general principle of restoring forces that you always return to equilibrium. And that's regardless, and that's even if there are other forces present. Now, you know that from experience, and this is the first time we've seen that, but that's something I had filed away in the back of my mind when I set this up. So the combination of gravity and the spring force wound up creating an effective force that looks just like the spring force. But here now, this is just truly being a restoring force. It is the net force of gravity and the spring force, but it looks just like our spring in the horizontal case from before. And that's what I mean by that. All right, let's maybe go and take a look at a bit of a different example. Earlier, when I was mentioning Cavendish's experiment, I mentioned how you hung some lead masses to attract other lead masses, and that caused a quartz fiber to twist. And by measuring the twist, we could figure out the torque the quartz fiber exerted. So here is a way that you can measure the what's called the torsion constant of the pendulum. Torsion constant of the wire. And that's by creating a contraption called a torsion pendulum. So the idea basically goes like this. I've got, this is my wire, or it could be a rod, whatever. Something that can twist. And then I usually you use a disc, but you don't have to. If you go online, you can look up these things called anniversary clocks, and you can see that instead of having a disc, you've got kind of an ornate combination of spokes with little spheres hanging out of them. But if you're actually trying to measure torsion constant, usually use a disc. And so the idea is you just go ahead and give this thing a known twist. And so what will happen is this will oscillate between an angle plus capital theta and angle minus capital theta. And to draw a capital theta as opposed to a lowercase one, you basically stick a tiny little h inside a big circle. All right. And this would be my equilibrium position. So we'll measure theta as the angle we're twisted off of the axis. So the torque that this rod or wire will exert will be a restoring torque. So this is not a K, this is a lowercase Greek kappa. Just as a quick reminder, you draw one of those like that. And so what this is saying is that the torque that this rod will exert is directly proportional to how much I've twisted it. Why the minus sign? Well, if I twist it counterclockwise, the restoring torque will be clockwise. And if I twist it clockwise, the restoring torque will be counterclockwise. So I need a minus sign there. Okay. And this is my torsion constant. So I can go ahead and do Newton's second law applied to rotations here and say that the torque here will be equal to I times alpha. It'll be minus kappa theta. I can rearrange to get that alpha is minus kappa over I times theta. Then I remember that the angular acceleration is the second derivative of position with respect to time. And right there we say, hey, that's the magic form. Second derivative of stuff equals minus crap times stuff. So this is a simple harmonic oscillator, and this is omega squared. So now we can say that the natural frequency, omega is equal to the square root of kappa over I. Now the way you would measure the torsion constant is you would have a disk of known moment of inertia. You would go ahead and remember that omega is going to be 2 pi over the period. So you give the thing a twist, measure the period, figure out omega, you know I, you can solve for kappa. You then use that to plug into the Cavendish balance experiment so that you know what the torque is that gravity was exerting on the setup. Now, we can go ahead and take this a little further. We can take a look at a system called the physical pendulum. Now here it's going to turn out that we'll have a harmonic oscillator, but not a simple harmonic oscillator, but we can make it act like one in certain cases. So with the physical pendulum, what we imagine here is that we have just some sort of irregular shaped object, maybe something like that. And we'll go ahead and mark where its center of mass is. And we will say that is constrained to rotate around this axis right here. Just following the notation that everybody uses, even though it's not a height, pretty much everyone calls the distance from the axis to the center of mass h. And so we'll go ahead and look at this and say that we are being twisted through some angle theta, like so. Well, there are two forces acting on the problem. There will be a normal force from the pivot, like so, and there will be a force of gravity that acts at the center of mass. Now, the normal force will exert no torque. Gravity will. This distance here will be my lever arm. So if this angle is theta here, my lever arm, our perpendicular, will be equal to h sine theta. So the torque that gravity exerts here, since I've twisted this clockwise, the torque will be counterclockwise, so there's a minus sign. Sorry, twist it counterclockwise, so the torque will be clockwise, and so you have to have a minus sign. It will be minus mgh. Well, we'll say minus fg. Then h sine theta is my lever arm. So I can rewrite this. Newton's second law applied to rotation is going to say this is equal to I alpha, and the force of gravity is mg. So I can rearrange this to get that alpha equals minus mgh over I sine theta, and this does not match our pattern. I mean, yes, it's the case that this is d squared theta dt squared, but I have to have theta. It's not going to cut it for this to be sine theta over here, but it's oh so close. Now, the correct answer for this is a horrible beast called an incomplete elliptic integral of the first kind, which, yes, a first kind implies the existence of an incomplete elliptic integral of the second kind, and incomplete elliptic integrals imply the existence of complete elliptic integrals. Now, I'll just say these things are nasty beasts. But you can start to look and say, is there any way I can cheat this a bit? Is there some way I can coax this into the form I know? And the answer is yes. What if we keep the angle small? So we can make what's called the small angle approximation. So if you go ahead and do a Maclaurin expansion of sine theta, you remember that that will be equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7 over 7 factorial plus minus da da da, like that. Now here's the trick. Remember, first off, we're working in radians here. So you say, well, what if, let's just say that theta is 1/10 of a radian. So a radian's about 57 degrees, so we're saying on the order of about 6 degrees or so. If we make theta 1/10 of a radian, then sine theta will be 0.1. And then this is going to be minus 0.1 cubed over 3 factorial is 6. And this is going to be plus 0.1 to the 5th. 5 factorial is 120. And I'm actually not going to bother with the rest of this. And that's because this is 0.1. This is going to be minus 0.001 over 6. It's going to be plus 0.00001 over 120, etc. This is absurdly small. And even this is less than 1/1000th. So the difference, so even here, for the most part, we can get away with saying, unless we're doing super duper fussy calculations, for the most part, we can just wish this term away. And so what we can say is, as long as the angle's kind of small, we can replace the sine of theta with theta itself. And again, depending how fussy you want to be, in a lot of practical applications, you'll still be making totally acceptable errors all the way out to about 0.3 radians or about 20 degrees. So as long as if we just agree to keep the angle small, and how small is small depends on how fussy you want to be, but small enough that these correction terms don't matter. We can then say that our second derivative theta with respect to time is approximately, and here we'll replace the sine theta with just plain theta, minus mgh over I times theta itself. And that gets it into the canonical form. We can now look at this and say, hey, this is a simple harmonic oscillator, and this is omega squared. So as long as the angle is small enough that it doesn't matter for what we're doing, and in a lot of practical cases, that's about 20 degrees or so, we have a simple harmonic oscillator that is has an angular frequency of mgh over I. So let's just try this. Let's make and see what we would get for, say, the period of a meter stick. If you say we're to take a meter stick and just very loosely hold it right at the very end to let it swing freely about the end, what would the period be? Well, we remember that omega is 2 pi f, so it's also 2 pi over the period. So we can take this result and say 2 pi over the period equals mgh over I, take the square root. So first thing we need to do is locate the center of mass of our meter stick. Well, if we say that our meter stick is of length L, just keep it nice and general, we'll stick in 1 meter at the end. Then H, BL over 2. All right. So this will be square root of mgl over 2. And the moment of inertia of a meter stick, we can treat that as a long, thin rod. And we remember that the moment of inertia for a long, thin rod is 1/3 ml squared. All right. So interestingly, the length of the meter stick matters, but the mass doesn't. But we still lose 1 power there. So 2 pi over t equals the square root of 3g over 2l. So rearranging, we can get that the period is 2 pi times the square root of 2l over 3g. If I put in 1 meter for L, and we say that this is swinging on the Earth, this will be 9.8 newtons per kilogram, which that's the same difference as meter per second squared. Meters cancel, have 1 over second squared, which is second squared. Take the square root of seconds, so that all works. Yay. And the time it'll take to do 1 complete swing back and forth is 1.64 seconds. Try it yourself and see. If you do a yardstick, it'll be a little shorter, just because a yard is a little shorter than a meter. And continuing on our journey of recycling results, the physicist's favorite trick, we can then take a look at a simple pendulum. A simple pendulum is just plain where you attach a heavy pendulum bob, any kind of mass will do, at the end of a string. So and we make the string effectively massless. So in that case, this distance here, h, is just L, because the distance to the center of mass is the length of the string. We can just recycle our result for the simple pendulum, again with the same caveat that we won't swing this more than about 20-ish degrees or so, depending how fussy we want to be. So this is mgh over I. H is equal to L. And if this is small enough compared to this distance that we can treat as a point mass, the moment of inertia of a point mass is ml squared. Cancel, cancel, cancel. We get that omega is equal to root g over L. So this is actually kind of a handy fact because, if, God forbid, you were ever kidnapped by space aliens and taken to some distant planet, you could improvise a pendulum, and using your watch, you could time the period that it swung to figure out the gravitational field strength so that when you finally figure out how to radio the Galactic Patrol, you can tell them what G is, and then they'll figure out what planet you're on, and that will definitely help speed up the search and rescue process. News you can use. But on a more serious note, let's take a look at a proposal made by Thomas Jefferson when he was thinking about possibly redefining the units that the United States was using. And this was before the French Revolution, so the metric system hadn't been thought of yet. For similar reasons as the French, he wasn't totally where the French wanted to get rid of any royal decree being behind their units and let the earth and dictate the units, which eventually the new SI became the universe itself dictating the units. Jefferson, for similar political reasons, wanted to redefine the units we were using in the United States so that we didn't have to be referring to yardsticks that were being kept in London. So an idea he had was a thing called the seconds pendulum. And what he was proposing was that the length of a simple pendulum, such that its period was 1 second, would be the standard of length for the new United States. Well, how long is that? Let's go take a quick look. We can remember that omega, which is 2 pi over the period, here's going to be root g over L. We're looking to solve for L, so square both sides. 4 pi squared over t squared equals g over L. Then rearranging, we get that L is gt squared over 4 pi squared. So this would be 9.8 newtons per kilogram. Times 1 second, because that's what he wanted it to be, over 4 pi squared. Newton per kilogram is meter per second squared. I have seconds squared. That gives me meters. And if you punch it through, you get 0.248 meters. So by comparison, a foot is, by law, 0.3048 meters. Or we could say that this distance was about 0.76, or say 9.76. Call it 9 3/4 inches. So that was, if Jefferson's proposal had been successful. I don't know what he was going to call that unit, but he was proposing basically letting nature dictate the unit based on how long the second is. Kind of funny thing, that's what we do now with the meter, since the meter is defined via the speed of light. Alrighty, so in the next video we'll go ahead and close out this treatment by taking a look at damping and driving. Catch you over there.